Anyways, today we are going to. Okay, by the way, have you checked the note? I have sent the PDF, by the way. Have you written them? I would suggest you to write them down. Ah, okay, no problem. And the videos, have you received the videos from Shobra sir? The record. Uh, okay. I mean, if there is any, do you want, okay, fine. Just ask him again, okay? And if he doesn't, then I'm going to, provide them in my YouTube channel. Is it okay for you? Okay, no problem. So I wanted to give it before, but Rakshit never didn't want it, so that's why I did not. I'm not providing them. Anyways, let's start from where we have left. Polyesters. Now, if I talk about polyesters, there are two types of polymerization. We have addition and we have condensation reaction. Okay. Now, if I talk about condensation polymerization, the two most common types of condensation polymers are what? We have to remember that, which is polyesters and polyamides, which involve the formation of an ester or an amide. So, amide linkage, okay, you can ignore the linkage part, it's just that an ester is produced. So, for example, in a condensation polymerization, let's discuss condensation polymerization first. In condensation polymerization, there are two different monomers that add together and a small molecule is given off as a side product. now, now the name says it all. Condensation means water is involved, right? So that means the byproduct which will be produced, it's either going to be water or hydrochloric acid. See, these are examples of condensation polymerization reactions. You can clearly see that when carboxylic acid and alcohol reacts, we know that ester and water is produced. We saw this in the previous class, if I'm not wrong, right? It's the same thing. The byproduct ester is produced, or instead of ester, uh, HCl or hydrochloric acid is produced as a byproduct. I mean, if you just change the carboxylic acid to acyl chloride, the same thing will be produced. Ester is just that instead of uh, water, we'll have HCl will be produced as well. I can see that he cannot join. I don't know why. Anyways, let's continue. So we have the carboxylic acid plus alcohol. So what's it called? So if we change, instead of carboxylic acid, if we provide acyl chloride, the halide comes in the picture. And now instead of the H which used to join with OH, I mean the alcohol, the OH from carboxylic acid used to come, and from alcohol H used to come, right? And when they joined together, water was produced, isn't it? But in this case, with H, the acyl chlorides Cl comes out, and this H and Cl reacts to produce the byproduct HCl. Either ways, ester is produced. Did you understand? Okay. Did you understand why ester is produced in acyl chloride as well? You do realize that when Cl goes away, this part, and if I talk about carboxylic acid, it's kind of same, isn't it? Like when the OH goes away, this part and this part is same, right? This part of carboxylic acid and this part of acyl chloride is same, isn't it? So that means what? When it joins with alcohol, the same product is supposed to be produced, isn't it? Ester, right? Okay. So if we have the same functional group on each end of molecule, we can make polymers. So we have the analogous equations. We have dicarboxylic acid. Again, it's the same thing. It's just that instead of alcohol, we are now using a diol. Basically, and it is a type of alcohol which consists of two hydroxyl groups. Okay, and carboxylic acid is the same thing. It contains double functional group of carboxylic acid. Okay, so there are two COOH. So what's going to be produced instead of an ester? Now a polyester, basically two ester molecules will join together to produce an polyester. Did you understand? Poly means many, right? Look, everything else is same basically. I hope you understood. One minute. Hello, can you hear me? Am I audible? Hello. Okay. Okay, fine. I'm continuing. Moving on to the next part, we have using the carboxylic acid to make the ester of or amide would need an acid catalyst and would only give an equilibrium mixture. The more reactive acyl chloride goes to completion and does not need a catalyst but does produce HCl fume. So what they're trying to say is that this reaction is not used like as instead of instead of acyl chloride, using carboxylic acid to produce ester is much more suitable way. Can you tell me why? Because the byproduct in that case is water, which is not toxic, right? But in the case of acyl chloride, HCl is produced as a byproduct, which is a toxic fume, isn't it? So this type of question might come in Unit 6. Do you understand? Some sorry, not easier. Which reaction is more suitable in is the correct term? I would say this is the better correct term. I mean this one. The using carboxylic acid and alcohol to produce ester. Okay, because if you use acyl chloride, what is produced? HCl is getting produced, isn't it? It's a toxic fume, right? So that's what I was saying. Okay, so that's gone. Now terylene, a common polyester. So terylene is this one, as you can clearly see. It's a name of a polyester. So as I said, how is a polyester produced? Dicarboxylic acid is required, isn't it? So this is an example for dicarboxylic acid. Okay, you can ignore this part. This part is known as benzene. We will learn this extensively back in Unit 5. Okay, we'll learn this in Unit 5. So you can ignore this for a while. Just understand that this is a dicarboxylic acid. Okay, see what is happening in the dicarboxylic acid when you're reacting with a diol. See, we all know what's a diol, an alcohol which is what, two OH groups, isn't it? So what is happening? We all know what's going to happen. The H and the H and the OH and the OH goes away. So we can clearly see what, two OH and two H, right? So what? How many water molecules will be produced here, sir? Exactly, two water molecules will be produced here. Now, the remaining part, will it stay like this? No, it's going to get attached. For example, where the part where where this part, where the part where the OH goes away from here, this one is gonna, this one is gonna get added to this part down here. Did you understand? And they did not show the right and the left part, which basically means that what it continues. Am I clear? The molecule kind of expands in both sides. Did you understand? Let us basically shoot a part of the polyester. Okay. Now, if you want to show that whether it extends in both sides, see, these brackets must be used. What do these brackets indicate? Indicate that this indicate that the molecule expands and this is the repeat unit. Am I clear? That means this part here is known as the repeat unit. You know what's a repeat unit, right? Basically, in a long chain of polyester, the unit which repeats itself after, like for example, we'll see the same unit being repeated from this part. We'll see the same unit being repeated from this part. Am I clear? So in order to indicate that, we are just using two third brackets. Did you understand? Exactly. So it's a big long chain. It's just that this is the part of it. Anyways, this is another example. You can clearly see this time they have used an diacyl chloride. Do you see? They have used a dichloride. See, they have used a diacyl dichloride here. Pentanediol dichloride, basically. That's what they are claiming. Somebody wanted to join but left again. I don't know why. uh, okay, anyways, let him join again, then we'll see. So this is pentane diol dichloride. Hello Rakshit, can you hear me? Hello Rakshit, can you hear me? I think he's not being able to hear me. Okay, anyways, let me just continue. What is even companion bed? uh okay, anyways, let me just continue. Rakshit, can you hear me? I think you can hear me. Anyways, so what I was trying to say, uh so this is what it happens when you react. The same thing is getting produced, a polyester is getting produced. Okay, I hope you understood. So moving on to the next part, this one. It is also possible for polyamides and polyesters to form one monomer if that monomer contains both the functional groups needed to react. So what they're trying to say here is that, for example, we have 2-hydroxypropanoic acid. Okay, so this is 2-hydroxypropanoic acid. You can see down here. More popularly, it is known as lactic acid. So we can clearly see we can like we can use one monomer. Like from this also, there is another way we can produce a polyester or a polyacid if you want, and that is from here. So have you noticed here what is happening? That the OH goes away from here while the H goes away from here. Okay, did you understand, Ikra? What is happening down here? The OH goes away and the H goes away from here, and they are joined. For example, you can clearly see this one, right? You can clearly see this part is basically what? This, right? Yeah, this part. And what is happening down here, sir? When this OH goes away, the other part, the another more, hydroxypropanoic acids, this part, the part where the OH is left, that part joins, isn't it? Did you see that? Exactly, like this part up to this part down here. So these two join together, and like this, the polylactic acid or a polyacid is getting produced. Okay, so that's how it goes. And by the way, there are three repeating units. You can clearly see this is one repeating unit. You have another repeating unit down here. Also you have another repeating unit down here, right? Three repeating units, that's why. Okay, if I talk about this one, 4-hydroxypentanoic acid, is the same thing. It's just that you can clearly see what, you can clearly see that here the OH is getting away. You can clearly see the OH is getting away from here, and the H is getting I think 8, yeah, the H is getting away from here. Okay, see what is happening. This one basically came here, like they just rotated it. Like what they did is pretty simple. They rotated it. Basically they brought this one down, and this kind of took this one up. See this one, and this kind of made this one, I mean this kind of made this one down. Okay, so that is why the H went away, and that's why they showed like this. Did you understand? Yeah, exactly. Also, it is possible for some of these compounds to form various cyclic esters under different conditions from forming the polymer. You do not need to learn these, but may be asked to deduce structure from the information given. Like, yeah, uh, like some of them can produce cyclic ester. Like, you can clearly see that this acid down here, you can see, right? Like they can this what is this? This is like a ester, isn't it? Like you can if you join this part, like if you join this part down here, it becomes an ester, isn't it? So that one, I mean what they're trying to say is that the same thing gets produced but in cyclic form sometimes, but it's very rare basically. Okay, so you don't have to remember this, just for clarification they told you. Then if I talk about the chemical reactivity of condensation polymers, now polyesters can be broken down by hydrolysis and are therefore biodegradable. Okay, this is an important stuff. They can be broken down by hydrolysis and are therefore biodegradable. What is, we know what's hydrolysis, right? Using water to break down, right? I mean, it kind of makes sense, doesn't it? See, we saw a little while back how a polyester is being produced, isn't it? So if we do the reverse reaction, what is the reverse reaction? The reverse reaction is hydrolysis, isn't it? Right? And the forward reaction is condensation. So see, we are using water in order to break this down in order to produce the diol and the dicarboxylic acid again. So I hope you understood now what's hydrolysis. And biodegradable means what? Okay, biodegradable basically means that they can be they can be decomposed by bacteria and other and fungi present in the environment. Okay, because if they are not decomposed, if they are not decomposed or not decomposable by natural decomposers like fungi or bacteria, then it's going to pollute the environment, isn't it? Like, think about it. In the ground, we have kept some polyesters or polymers. We expect it to degrade, or with time we expect it to get decomposed by fungi and bacteria. Now if it's non biodegradable, won't that be a problem? Hmm? Isn't it polluting and taking up space in the ground? So that is why polyesters are biodegradable and economic friendly. Okay, not economic, in other words eco friendly, more better word. Polyesters can be hydrolyzed by acid and alkali. With HCl, a polyester will be hydrolyzed and split up into the original dicarboxylic acid and diol. With NaOH, and polyester will be hydrolyzed and split up into diol and dicarboxylic acid salt. Okay, one thing's pretty clear. I think they made a mistake here. That is, did they? Yeah, they made a mistake here. Not a dicarboxylic acid. Rather than with HCl, we saw a little while back what will be produced. A diacyl dichloride will be produced. Did you understand why they made a mistake here, Ikra? Diacyl dichloride and diol will be produced. Okay, that's how it goes. And this part is pretty simple. Obviously a diol and a dicarboxylic acid salt. Well, by the meaning of salt, they basically mean here that the Na joins, okay, instead of H. Did you understand? Like, you can clearly see if I say, like, do you see this part down here? Instead of this OH and OH, Na joins. Did you understand? Actually, not two, only one Na joins. Sorry. So that becomes a salt basically, okay, instead of a dicarboxylic acid. Now, the next part and the most crucial part that you are going to start, and we are going to move up the technical side of organic chemistry in A2, which is spectroscopy and chromatography. Chromatography is something which is very much, unknown to a lot of chemistry students in AS level as well as in A2 level. You have learned this in IGCC, but obviously in a simplified format. In this case, we are going to go deep. I mean, in A2, we are going to go deep in chromatography and what are the different and the various methods in which chromatography is performed. The procedure is very much important to understand, considering they will ask you to write the procedure as well as ask you questions from the procedure, that why this was done, why this was required, and whatnot. Mostly in Unit 6, but it is also important in Unit 4 as well. Okay, so the effect of different types of radiation in molecules. Okay, what is spectroscopy? Basically using radiations in order to analyze, you know, different types of organic compounds or molecules. Okay, so what are radiations? There are different types of radiations. Electromagnetic waves are basically known as radiation. Waves are radiation basically, right? What is radiation? Basically just the definition of waves. What are waves? Medium of energy transfers, isn't it? Some simple physics. So the things that are required here, first things first, will be requiring infrared analysis. Will also be requiring ultraviolet, radiation, uh, and of course radio waves, which is very much important in NMR. What is NMR? We'll understand later, and microwaves. So thing about I think we have infrared spectroscopy. The thing about infrared spectroscopy, we learned this back in AS, right? Remember we learned IR in spectroscopy. Hello. Yeah, so that's what they're trying to say here. So what does infrared energy does? It basically causes the bonds to vibrate, which the vibration is measured in what? We saw that in IR spectroscopy. We saw the vibration was measured in uh, transmittance, and then there was a wave number, right? Hmm? Exactly, wave number. What is wave number? It is basically reciprocal of wavelength. All right, so we saw this back in AS. So yeah, that's how infrared waves is required in spectroscopy. If I talk about ultraviolet radiation, remember initiation reaction in free radical substitution reaction, we required UV energy to break the bonds in ClCl or CCl bond, right? Like this kind of provides the energy to initiate the reaction. The sole reason, and it's also the core reason why the first step of free radical substitution reaction is also known as initiation, right? Now, the main thing that we're going to deal into is about radio waves and, of course, microwaves. See, radio waves have a particular, feature or a trait. They can cause the hydrogen nucleus to change its spin state. This can give us information about the arrangements of hydrogen in a molecule. Change the spin state means, if I go in atomic scale or if I speak in atomic scale, uh, okay, if I talk in atomic scale, uh, we know, I mean, we kind of know that at the center we have the nucleus, and inside the nucleus what do we have? We have protons and neutrons, and around it we have what? Those famous electrons, right? The orbitals which containing the electrons, isn't it? Now these electrons are present. We came in AS and we learned what? These electrons are now present in orbitals, isn't it? Orbitals could be spherical. We saw this. S orbitals are what? Sphericals, isn't it? Then orbitals could be dumbbell shape, right? D orbitals. Now, within these orbitals, electrons are present. We know that. Like there might be an electron present here, and there might be an electron present there. All right. Let's consider this is a d orbital. We have two electrons, and we know that each orbital can consist up to two electrons or contain up to two electrons. Now, these electrons tend to spin. Okay, these electrons tend to spin in their position. One tends to spin in opposite side. For example, let's say anti-clockwise, and the other tends to spin in the clockwise direction. There was a rule. Do you remember the Pauli exclusion principle rule? What does it signify? The Pauli exclusion. Okay, yeah, Rakshit, do you know what's the Pauli exclusion principle? There were two rules by the Hund's rule and Pauli exclusion principle. You don't know the Pauli exclusion? Did Oh no. It was there in the AS book, if I remember. In the Hund's rule, what was the Hund's rule? The Hund's rules stated that electrons would occupy those orbitals of lower energy first before they occupy the higher energy orbitals. And the Pauli exclusion principle stated that electrons of the same spin cannot occupy the same orbital at the same time. So we saw this in the box notation format, how you used to represent electron spin, right? Like this one is something like this. What does this indicate? This indicates that both of the electrons present in a specific orbital are present in opposite spin, or are spinning at opposite directions. Pauli exclusion principle forbids two electrons to be present at together with the same spin. Did you understand? Like this is not correct. Do you understand? So that's what I'm trying to say here, that we're in an orbital when two electrons are present, they tend to spin at opposite direction. One goes in anti-clockwise and one goes in clockwise. Now this unique thing about radio waves is that they have this capability to change its spin state. What they're trying to say is that they have the energy, or they provide the necessary energy to change the spinning direction of an electron. So you can say that this electron basically rotates in clockwise. It's rotating clockwise, and with the induction of radio waves, it started spinning clockwise, sorry, anti-clockwise, like just like this one. Okay, that's what they're trying to say here. Did you understand? Okay, now there is a fun thing here. That's wanted to let you know. If both electrons spin at same directions, energy is released. The reason why is pretty simple. The what's it called? The charges add up. But if, or in other words, energy is released, or if I talk about better way, magnetic energy is produced if both electrons spin at opposite directions. Magnetic energy is uh, what's it called, vanished, or it just goes away. Okay, magnetic energy basically means dipole. Okay, magnetic dipole, it's also known as magnetic dipole. Now why this is important, we'll understand a little while back later. So just wanted to let you know there is a reason why you know in a lot of cases, like if I talk about iron, there is a reason why iron is not magnetic in many cases. There are some scenarios in which you can use radio waves in order to create it, in order to convert iron into a magnetic material. Okay, how? Like this. So I have provided you the core reason of how you can make anything magnetic. Did you understand? So basically how magnetic energy is produced, I provided the main reason in atomic scale, that it's all about the spinning of electron direction. Okay, if they're in the same side, then magnetic energy will be produced. If they're in the opposite direction, magnetic energy won't be produced, regardless of any material, because we know in any everything is made of atoms. Okay, so that's what it kind of differentiates. uh, let's talk about NMR spectroscopy. NMR spectroscopy involves the interaction of materials with low energy radio wave region from the electromagnetic spectrum. Okay, look what it is done. The radio waves used in the proton NMR cause the hydrogen nucleus to change its spin state. Okay, its spinning state changes. Okay, so just as I said, if the if all the electrons now basically start changing their spinning, then obviously the nucleus is also going to change its spinning state as well. So just want to let you know that the the spinning direction of the nucleus ultimately is determined by the spinning direction of the electrons. Okay, so that's how it goes. So eventually the nucleus spinning state is going to change as well. So everything is spinning basically. Okay, because nucleus is also made up of what? Subatomic particles, isn't it? Just like electron, proton and neutrons are also spinning at their own orbitals basically. Okay, it's just that the thing is that their spinning direction is kind of dictated by the direction of the spinning direction of electrons, considering because the spinning direction of electrons produces the energy to spin the, what's it called, the nucleus's spinning direction. Okay, so every subatomic particle in chemistry or any atom are in the are always constantly spinning at every moment of time. Did you understand? This is something this is a you don't have to understand that deep, because these concepts are directly taken from quantum chemistry or quantum physics. Did you understand? Okay. Now, NMR spectroscopy is the same technology that is used in magnetic resonance imaging. I think you have heard about MRI, right? There is this big machine where people sit in a stretcher, and the stretcher is basically, you know, uh, you know, taken in inside the, big tube, the MRI tube. Have you seen that MRI tube in diagnostic centers and medical centers, right? The sketcher, and the human body is placed in a stretcher, and the stretcher is placed inside the tube, and that is what basically is that is what basically MRI is. It's known as magnetic resonance imaging. It tends to provide us, it helps to provide us diagnostic information about internal structures in body scanners. For example, scanning for brain disorders. A very popular application of MRI is finding is creating images or diagnostic images of our brain. So it tends to capture brain activity very nicely in HD format. And by analyzing the brain activity, doctors can provide you a very nice in-depth diagnosis or prognosis about your psychological activity, or your or whether you have any brain disease or not. Okay, so the whole thing, NMR spectroscopy, the technology is basically is the same technology which is used in MRI. Okay, so how you don't have to go that deep. If you under this part, if you study or if you have bachelor's in biomedical engineering, then you can go deep. Like in biomedical engineering, they're just going to explain you this whole thing in a much more advanced format. Anyways, uh, let's move on to the part which is very important for our syllabus: equivalent hydrogen atoms. Oh, by the way, Rakshit, it's already 6. Will you leave now or will you stay? You said you had a class or something. Oh, I see. Okay, fine. That's okay. So if I talk about hydrogen atoms here, in an hydrogen NMR spectrum, there is one signal for each set of equivalent hydrogen atom. So if I talk about ethanol here, so I need to talk about it very nicely. Okay, so in if I in short words, if I say uh, what is NMR spectroscopy, or how the NMR spectro the application is basically required here. Okay, so if I give you an example down here, we need to identify the number of hydrogen environments present in a particular organic structure. Okay, this is what it matters. For example, we can clearly see that H, these three hydrogen atoms are connected to the same carbon, isn't it? Right? So can we consider them as all of them as hydrogen environment A? Hydrogen environment A. We can consider them as hydrogen environment A. If I talk about these two hydrogens are attached to the same carbon. So these is another environment, and of course we have the last one, our lonely guy, the only another lonely environment, hydrogen environment, which is connected to oxygen. So in total, we can see that ethanol has three groups of different hydrogen atoms, or three groups of different hydrogen atom environments. Okay, and depending on that, we will get to see the peaks in the spectrum. So look, this is a nice example, I believe. uh, for example, check out this one down here. We have what, this is another example, this is another structure, I believe. So in this structure, you can clearly see this is one hydrogen environment, this is another, this is another, this is another, this is another. Okay, by the way, why can anybody tell me, like, why this environment's hydrogen atoms and this environment's hydrogen atoms are the same thing? Can you tell me why? Yeah, they have the same hydrogen. It's just that they're connected to the same carbon. You see that? That's why basically. Okay, and you can clearly see that uh, this carbon and this carbon down here, they're even the hydrogen atoms which are connected to these two carbons, they're kind of connected to the same carbons. That is why, you know, they have they're part of the same hydrogen atom. Okay, so thing about this NMR spectroscopy is that you have to identify the number of unique hydrogen environments. That's the main thing. Okay, if you can identify that, then understanding from the pics is pretty simple. See, this is another thing. So we have okay, this is see in this, with this carbon we can clearly see that we have this carbon, right? And all the hydrogen atoms connected to each of these carbons are part of the same clan, isn't it? C, right? And then you can clearly see this one. This is another hydrogen environment. Okay, how let me describe it in a much more nicer fashion. Mm, see this carbon, the hydrogen atoms connected with this carbon, they're connected with this, right? So this is one environment. Now think about why these two hydrogen atoms connected to this carbon are in a different environment. Because think about it, in the left side they're connected to another carbon which is part of another hydrogen environment, and it's connected, and in the right side also the carbon which is present in the right side of this carbon, that is also present in another environment. So obviously this also makes it itself another hydrogen environment. Did you understand? Now, if I think about this one and this one, check out this one and check out this one down here. Don't they have the same? Aren't they attached to the same carbon or with the same environment? So that is why they are part of the same clan. Rakshit, did you understand? Yeah, this identifying thing is a new thing. You have to understand the identifying concept. If you can identify it clearly, then it's gonna be pretty easy. See, this is also simple. This is another environment. You can clearly see it's connected with oxygen. So yeah, again, this is another environment. Okay, why this is another environment? Even though both of them are connected with the same functional group, did you understand why? Because of this. All right, the left side, it has a different environment in the left side, but yeah, it does, even though there is nothing in the right side, but it's gonna that is why this is another environment and this is why it is another environment. So you have to understand, if there was nothing, like, think about it, if there was nothing here and if we had something like CH3 down here. Okay, if we had CH3 down here, then I would say that both of them would have been what? In the same environment, right? These six hydrogen atoms that you see down here, they would have been in the same environment. Did you understand? Okay. So we have three sets of equivalent hydrogen. Okay, by the way, there is a thing called ratio. What does the ratio represent? Well, the ratio basically represents the number of hydrogen atoms. The ratio represents the number of hydrogen atoms present in each unique hydrogen environment. So I think you can clearly understand 3 is to 2 is to 3, 3 to 3, right? So it's that simple. Okay, check out in this one why there are four, hydrogen environments. Yeah, this is one hydrogen environment. That is obviously another hydrogen environment, considering it is, if a left side and right side is not same. This is obviously another hydrogen environment, considering left side and right side is again not same, right? You can clearly see it there, right? So that's how it goes. I mean, you might be a little bit confused that, sir, we have the carbon here, it has CH3 and CH2 down, and in here it has CH and CH3. So obviously the environments are not same. So obviously this is another unique environment. And last but not the least, this one is also obviously, it is in the another environment. Why it is another environment? Because you can clearly see this one is connected to a CH and this one is connected to a CH2. Well, if it would have been connected to a CH, then this one and this one would have been part of the same clan. Did you understand why they're unique? Hmm? Hello? Okay. And I guess you can understand the ratio thingy. The ratio is pretty simple. Well, we have 3 down here, we have 1 here, we have 2 here, we have 3 here. See, that's the ratio. Again, you can clearly see here and here the same thing. Basically, you can clearly see out here. I hope there's nothing to be nothing to understand. It's pretty simple. Okay. Now solvents are dissolved. Now how does this, like, there must be a process or a method in which NMR spectroscopy is done, right? So at first, what is done, for example, these samples which we have analyzed a little while back, at first these samples are dissolved in solvents which do not have any hydrogen atoms. Now this is very 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 important. Why this is very important? Because if if we would have dissolved them in solvents consisting of hydrogen atoms, they would have itself released signals. The solvents if the solvents contained hydrogen atoms, then they would have released signals which would have contradicted or interfered with the signals coming out from the environment of the main sample. Did you understand why we are using solvents without hydrogen atoms? Examples are pretty simple. The examples of the solvents are CCl4 and CdCl3. All right. This means what? This means that in the hydrogen NMR spectrum, the solvent will not give any peaks. At least that's we have to ensure. Okay, we need to ensure that only the peaks which are provided in the spectrum are coming out from the signals which are obtained from the sample which we have dissolved. Do you understand? Hmm? Okay. Now the spectrum which we are longing to talk about, we'll see that down here. Now see, spectrum consists of two parts. We have a peak. Okay, we have a peak like this. Okay, and we have in the x-axis something known as chemical shift. Now chemical shift is measured in ppm, something which we have learned in as as well, right? What is it? Parts per parts wait 1 minute. Parts per million. Okay. Now good thing about parts per million is that this will be provided in your data booklet. Okay, this part here, it will be provided in your data booklet. You don't have to worry about that. See, this is a typical data booklet value. We have some you know structures provided. For example, this for example this environment. Okay, for this hydrogen environment, we will have a ppm between here. For this hydrogen environment, particular hydrogen environment, we'll have a ppm between this range. Okay, so and so on and so forth. Okay, see, now this is very much important. At first, for example, uh, they might provide you for example, at first they might provide you they might provide you two things. Okay, they might provide you the structure and they might ask you to identify the number of unique environments, or they might not provide you this. Instead, they might provide you this spectrum down here. So we have how many peaks here? Well, we can clearly see that we have 1 2 3, if I'm not wrong. Sorry, 1 minute, did I make a mistake? 1 minute, not this. Okay. Oh, a little while. 1 minute. Let me show you a spectrum from the book. Then it will be much more easier to understand. This one is a little bit, you know, advanced. See, this is important. 1 minute. Okay. I think you can see the book, right? Can you see the book? See, I'll explain it from here, then it's going to be much more easier. So this is an example of a hydrogen NMR spectrum. Now there are two types of hydrogen NMR. The reason why I brought you here, this is known as a low resolution hydrogen NMR spectrum. Okay, see, we have the chemical shift in the x-axis and we have the peaks down here. What did I say? The peaks represent what? The number of peaks tells you the number of different chemical environments of the hydrogen atoms in the molecule. In other words, they represent the number of what? Unique hydrogen peaks which we have seen, unique hydrogen environments which we have identified in the structure, right? I showed you a little while back. Unique hydrogen environments. Okay, it's written down here. And another thing is that the area under the peak represents the relative number of hydrogen atoms in each environment. Basically, the circular thing that you see down here, these basically represent the area under the peak, or in other words, they represent the number of hydrogen atoms present in each respective environment. Okay, so that is what matters basically. What is this? Okay, what is there is an issue. 1 minute. Mm. Okay, in this case, if I say down here, okay, so this where I was, yeah. So this basically represent the number of hydrogen, environment, atoms in each environment. Now this part here I wanted to explain. See, this is the graph which will be provided in your data booklet, so you don't have to worry about that. See, it kind of represents the chemical shift and the corresponding, hydrogen environments found in different types of, organic compounds present in the, that we'll encounter in our A2 chemistry syllabus. Okay, for instance, if you get to see a peak with a chemical shift between 2.0 and 4.0, and if there are other evidences, for example, if you see there is only one hydrogen, I mean, they will provide you some clues basically. So if all the clues along with the chemical shift identified from your spectrum provided indicate that it is between that it is something which is between 2.2 to 4, and it is indicating an alcohol, then it will be an alcohol. Okay, so that is how you have to identify the structure or the environment, in the, or basically the you have to identify the environment basically in the structure provided in your question. So if you identify all the hydrogen environments, you will notice that when you join those environments, you will get to produce a nice structure. Okay, look, for example, if I give nice and AJ, yeah, this one. Look, this is butanol and butanol. So we can use the chart to interpret the low resolution hydrogen NMR spectra of these isomers with the molecular formula C4H8O. So we clearly know that for butanol and butanone the molecular formula is similar, isn't it? C4H8O. Now this spectrum basically shows the spectrum for butanol. I think we are familiar with butanol, right? I'm not writing it down. You understand what's butanol? Okay, let me just show it there. It'll be much more simple. So I think you're familiar with this. So now they have provided here butanol, right? So I'm just gonna give this and CH2, CH3. Anyways, this is butanol. See, the peak at 9.8 ppm is within the aldehyde range. So must be due to the H in the CHO group. Wait, what? Let me bring the table that it's gonna be much more simpler to understand. Okay, so they said here the 9.8 peak. You can clearly see this is the 9.8 peak. It is within the aldehyde range, so it must be due to the H in the CHO group. Well, do we have it here as well? I think we do. You clearly see that 9.8 falls within the aldehyde range. Okay, so our first hydrogen environment detection is completed. Now the peak at 2.4 ppm. Where is 2.4? Somewhere here. This one is 2.4, I believe. Yes, is within the range for HCCO. So must be due to the two hydrogen atoms in the CH2 group joined in the CHO group. Well, must due to the two in the CH. So basically, they're trying to say this one. So if I say so, if I use some better, so this down here is this. This down here is this, and the next part. Okay, see the 2.4. See, from 2.4 we can clearly see down here. Oh, 1 minute. 2.4 falls here, right? Which is this one. That's what they're trying to say. You can clearly see the peak at 1.6 ppm. Where is 1.6 ppm? There, this one is 1.6 ppm. Is within the range for this alkane, which is 1.2. Yep, that's right, alkane. Which means what? So this must mean that the two hydrogen atoms in the CH group are not directly joined to the CHO group. So one thing's pretty clear. So by understanding, by using the peak to identify the hydrogen environment, we can understand, where the environment is connected, or which or with which carbon where the hydrogen environment is connected. So since we can clearly see this one an alkane, so it must be due to the two hydrogen atoms in the CH2 group which is not directly joined to the CHO group, basically this one, right? You can clearly see this kind of represents an alkane. See, this part and this part is, aren't these alkene? Ikra, are you understanding? Aren't these alkene environments? Rakshit, are you understanding why this CH2, why not this CH2, sir? Okay, so this one goes there. Okay, and the last one is, I guess, is pretty simple. The peak at 1.0 is within the, again, the same thing. So you can understand this one. This CH3 is this, and this one is obviously connected to, and CH2, which is obviously an alkene environment, or it's an alkene. I hope you understood. This type of questions will come. They might provide you the spectrum and tell you the, the name of the compound, and that's what you have to do. Or in other words, they might do the opposite. They might provide you the structure, okay? They might provide you the structure, and they might tell you to write this stuff. Did you understand? Exactly. So this type of questions will come. See, this is the application. Okay, I did not teach you guys the the quantum mechanics or sorry, the quantum physics part, the the spinning thingy. Okay, because that's not required. If I show you why it's not required, check this out down here in your book. It is provided nicely. A big full page has been dedicated for theoretical knowledge, for understanding theoretical knowledge, if I say so. uh, 1 minute, sir. See, this is the part I wanted to say. I'm not gonna. If you want, if you guys want, for curiosity, you can see. This is the part where they have talked about the theoretical aspect of C. It's written here. You do not need to revise the principles of NMR spectroscopy, as you will not be asked questions about it in your exam. So that is why I have not gone that much deep. But for curiosity, you guys can understand this. So this one, like right here, this table A that you see down here, this table A represents the theoretical part. How it basically goes deep of how NMR works. Okay, so if you guys want, you can understand. You can what's it called, during your free time. Delve into the theoretical stuff, or you can just keep it as it is. What I've explained so far. In next class, we are going to start high resolution proton NMR, and after that we are going to move on to chromatography. There are two types of chromatography: gas chromatography, and then there is another type of chromatography, and after that our organic will be over. Okay, so that's it up to this much today. Please provide me another day which you guys are free, because I was supposed to take 3 days, right? So can you tell me another day when you guys are free? Make sure that both of you are free during the same time then, so it's gonna be much more suitable for me to take the class. Tell me. Huh? Sorry? No, no, this is the second class. I did not take class yesterday. This is the compensation. Uh, how about I take another class at 19th Tuesday? Is it okay for you guys? Okay, I'm gonna take a class on Tuesday, and yeah, that's it for this week. Bye bye. And 1 minute, let me provide you guys the note up to how much I've taught you guys before you guys leave. It was from polyesters, right? Okay. 12 to 15. Okay. Oh, by the way, Rakshi, did you get the recording from Shubro? Please take it. And as I said, another thing that if you cannot, I mean, if he's too busy to provide, then I would suggest to, uh, the way I have told you that I will provide. What's the issue with YouTube? I mean, it's much more, convenient in my point of view. And how does Shubro provides you? Telegram? Okay, I'm thinking of I don't know. I'm doing something. I'm gonna upload all my recordings. I've taken 4 classes so far. I'm gonna upload 4 of the classes in my YouTube channel. I'm gonna keep it unlisted. I'm gonna provide you the whole playlist link. And if you guys want, Ikra obviously has no issue. Only you have issue. So if you want, you can check it out. It's up to you. I'm gonna just share it. Okay, no need to rely on somebody else. I'm pretty sure he's busy or some sort. Okay, and that's why he's constantly forgetting. All right. Yeah. Okay, so that's it for today. Bye bye.